Hello, everybody. In this video, we're going to talk about the January 2008 Prelim Problem 3. We're given a random sample x1 through xn from the exponential distribution with rate lambda. In part A, we want to find a regular old MLE, which should be very straightforward. In part B, we want to determine whether or not the MLE is efficient, which means we want to compute its variance and compare it to the Cromie-Rao lower bound. And in part C, we want to find another MLE, this time assuming we are not looking at the random sample, but instead another kind of piece of information. And I'll talk about that when we hit part C. So let's go. So as I was saying, part A is very straightforward. We want to write down the PDF for the exponential distribution. And then we want to form the joint PDF. And because these are IID random variables, we can get to the joint PDF by just multiplying together a bunch of individual PDFs. So we get lambda to the n, e to the minus lambda, the sum of the xi, and then a product of indicators. Now we want to form a likelihood. I'm going to call this L of lambda, and this is anything proportional to the joint PDF when thought of as a function of lambda. So for example, this multiplicative constant where we've got the product of indicators does not involve lambda, so we can drop that. And I'm going to take the likelihood to be lambda to the n, e to the minus lambda, the sum of the xi. And then to maximize this, that is the goal, and it's almost always easier to work with the log likelihood. But remember, the goal is to maximize it. And if working with the log of the likelihood does not make it easier, then don't look at the log of the likelihood. It tends to become habit because it's almost always easier. So people think of it sometimes as a step for finding the MLE, but you don't have to look at the log likelihood. To maximize this, I'm going to take the derivative with respect to lambda of the log likelihood. This is n over lambda minus the sum of the xi, and set it equal to 0. Then we want to solve for lambda, and that will be our MLE. We're going to put a hat on it and make it all capital. You can see that 1 over lambda here is going to be x bar. So solving for lambda, we get lambda hat is 1 over, I'm going to make it capital. This is my actual estimator, x bar. And we were told to call this actually lambda hat sub n. And that is the end of part A. I guess we should check that we did maximize it and did not minimize it. So if you look at the second derivative, you get minus n over lambda squared, which is always negative, which means that we have something that is concave down, and we did in fact maximize and not minimize the likelihood. Okay, in part B, we want to look at this MLE and figure out whether or not it is efficient. This means we want to compute its variance and figure out whether or not it achieves or equals the Cromie-Rao lower bound. Now, its variance could actually be lower than the Cromie-Rao lower bound because the Cromie-Rao lower bound is a lower bound on the variance of all unbiased estimators of lambda, and MLEs are not necessarily unbiased. And in fact, in this case, we're going to see that this MLE is not unbiased. So usually we talk about efficiency when we have an unbiased estimator, but we can still do this problem. We want to compute its variance and compare it to the Cromie-Rao lower bound. So what is the variance? The variance for the MLE is, I'm just going to plug in the MLE. This is 1 over x bar. So x bar as a sample mean of exponentials has a gamma distribution, and you might go straight for that. I personally think it's a little cleaner to take out the n and look at the sum of the x's. So I can write this as the variance of n over the sum as I goes from 1 to n of the x's. Then I can pull the n out and it will come out squared. And I'm left with the variance of 1 over the sum of the x's. So I'm going to call that W, where W has a gamma distribution, and I'm adding up exponentials. The first parameter is the number of exponentials, and the second parameter matches the rate parameter. So continuing this line above, we have n squared, and then we have the expected value of 1 over W all squared, which means W is squared, minus the expected value of 1 over W all squared. And so we need to find these two pieces. And for this problem to make sense, we do need n to be greater than or equal to 3, even though it doesn't say that, because the integrals are going to blow up otherwise. So the expected value of 1 over W, this is the integral from minus infinity to infinity of 1 over W times the PDF for W. But W has a gamma distribution and the support is 0 to infinity. In other words, that integral is going to zero out for all the negative W's you want to plug in there. 1 over W, then 1 over gamma of n, lambda to the n, W to the n minus 1, e to the minus lambda W, dW. So to do this, I'm going to bring the 1 over W in with the W to the n minus 1. This is the integral 0 to infinity, 1 over gamma of n, lambda to the n, W to the n minus 2, e to the minus lambda W, dW. So looking at just the kind of variable part of this integrand, this appears to be like a gamma n minus 1 lambda PDF. Now it's not quite that because I don't have the right constants, and to make it look like a gamma n minus 1 lambda PDF, I am going to need to have this 1 over gamma of n to be 1 over gamma n minus 1. I'm going to need this lambda to the n to be lambda to the n minus 1, and then I'm going to write the rest out. And obviously that's not equal to the line above. So I need to put in and, manage constants to make it equal to the line above, which means I'm going to need to put in front a gamma of n minus 1 over a gamma of n and pull out a single lambda. So that's what makes this line equal to the previous line. Now I am integrating a gamma n minus 1 lambda PDF, and that integral is going to be 1. So we get gamma n minus 1 over gamma n lambda. And because n is an integer, we can simplify this with factorials. So gamma of n is n minus 1 factorial. Similarly, gamma of n minus 1 is going to be n minus 2 factorial. We get a lambda sitting there, and we get a lot of cancellation. So we get 1 over n minus 1 lambda as the expected value of 1 over W. The expected value of 1 over W squared is very similar. W still has this gamma n comma lambda distribution. This is going to be the integral 0 to infinity 1 over W squared times that gamma n lambda PDF. So I'm going to combine the W's. And then if we look at the parts of this with a W in it, this looks like a gamma n minus 2 lambda PDF. It's not quite right. We don't have the right constants in front. So I'm going to play the same game of putting in and compensating for the constants so that we have an integral of a PDF that we know is 1. So I am going to need 1 over gamma of n minus 2 lambda to the n minus 2 W to the n minus 3, e to the minus lambda W, dW. And to make that equal to the previous line up here, I will need gamma of n minus 2 over gamma of n lambda squared. And this is the integral of the gamma PDF, so it's equal to 1. And we get gamma of n minus 2 over gamma of n lambda squared. So we can simplify this to be n minus 1 factorial, and on top here, n minus 3 factorial. So here's why we needed n to be greater than or equal to 3, or one of several reasons, because if it wasn't, then this would not integrate to 1 and would actually blow up. So this is 1 over n minus 1, n minus 2, lambda squared. So we're almost done with the variance of our MLE. This was n squared, the expected value of 1 over w squared, which we just computed, minus the expected value of 1 over w all squared, which we computed right just before this. We have n squared. So this has a lambda squared, and this has a lambda, which will end up squared. So I am going to go ahead and put a lambda squared out here. So as for this first one, I get 1 over n minus 1, n minus 2. And for the second one, I get 1 over n minus 1 squared. And getting a common denominator there, this is the common denominator is n minus 1 squared over n minus 2. And we get n minus 1 minus n minus 2. And we end up with n squared over n minus 1 squared, n minus 2 lambda squared as the variance of our estimator. So we're only halfway done with part B. We want to know if this is an efficient estimator. So we want to know if this actually equals the Cremier-Rao lower bound for lambda. Again, if this was an unbiased estimator, its variance could equal it, or otherwise it would need to be greater than the Cremier-Rao lower bound. For the MLE, in this particular case, our MLE was not unbiased, so comparing the variance to the Cremier-Rao lower bound, you could potentially get a variance smaller than the Cremier-Rao lower bound, in which case we would have what is called a super efficient estimator. The Cremier-Rao lower bound for a function tau of lambda is the derivative of tau of lambda squared over the so-called n-dimensional Fisher information. Here, we are estimating lambda itself. So when you take the derivative, you'll get 1. And so we get 1 squared over the n-dimensional Fisher information. And I'm going to use a simplifying fact here because these are IID random variables. The one-dimensional Fisher information can be written as n. The n-dimensional Fisher information can be written as n times the one-dimensional Fisher information. So let me remind you what that is. This is the expected value of the derivative with respect to lambda of the log of the PDF with x1 plugged in. And this whole thing gets squared. And that's also equal to the negative of the expected value of the second derivative of the log of the PDF. You can use either one of these and you'll get the same answer. Usually one formulation is more convenient than the other, so let's see what we have here. The PDF is lambda e to the minus lambda x. The log of the joint PDF is the log of lambda minus lambda x. And then the derivative with respect to lambda of the log is 1 over lambda minus x. I can already tell that the second derivative is going to be easier or a little less work, not much, but let's do both of these. The one-dimensional Fisher information is the expected value of this derivative. I want to plug in a capital X1 and square it. Otherwise, there's nothing to take nothing interesting to take the expectation of. This is the expected value of 1 over lambda minus x1 squared. Because it's squared, this is the expected value of x1 minus 1 over lambda. And because x1 has an exponential distribution with rate lambda, this is the mean of that distribution. So this is the variance of x1. And most Fisher information Fisher informations, most Fisher informations, most of them will come out to be a variance. And if not, you can usually adjust them to make them look like a variance. But the variance for the exponential distribution is 1 over lambda squared. So now I just wanted to really quick do the second version of Fisher information. So this is this is the negative of the expected value of, oops, I already have that negative, of the second derivative with respect to lambda of the log of f of x1 and lambda. And here is the first derivative. So when I take the second derivative with respect to lambda, I get negative 1 over lambda squared minus 0. So the x's are completely gone. And so the expected value, we're looking at the expected value of a constant. It's like the expected value of 5 is 5. We get negative 1 over lambda squared. So the one-dimensional Fisher information is 1 over lambda squared again. We got the same thing, which is always a good thing. The Cremier-Rao lower bound for the variance of all unbiased estimators of lambda is 1 squared over n times this one-dimensional Fisher information. That's going to be 1 squared over n over lambda squared, and that's going to be lambda squared over n. So we want to compare this to the variance of the estimator. The variance of our MLE estimator was n squared over n minus 1 squared, n minus 2 lambda squared. And we want to compare that to lambda squared over n. So obviously they both have a lambda squared, so we just want to look at the coefficients. If you want to start writing out a polynomial and figuring out whether or not this is greater than or equal to the 1 over n, that's fine. Otherwise, I think I might just look at this for a couple of values of n. When n is 1, the left side is, oh, that's not good. Remember, we did say that n had to be greater than or equal to 3. So when n is 3, the left side here is 9 over 4 times 1, or 9/4, and the coefficient on the right side is 1 over 3. And so the variance is clearly greater than or equal to the Cremier-Rao lower bound in that case. When n is 4, we get 16 over 9 times 2, which is 16 over 18. And on the right-hand side, we get 1/4, and still greater than or equal to. And I guess, you know, maybe if I was taking the prelim, I would draw a conclusion right now and then come back if I had time to actually prove that this coefficient is greater than or equal to 1 over n for all integers 3 and higher. So I just sort of gave us some evidence to believe that's true, but it appears, at least for n equals 3 and 4, and it is true for all n, that the variance of the lambda n hat is strictly greater than the Cremier-Rao lower bound for lambda, i.e., this is not an efficient estimator. Okay, we're ready for part C. So in part C, we do not observe the actual values of the data. Instead, it is known to us that k out of the n data values are less than or equal to a fixed constant capital M, and the remaining n minus k are greater than that capital M. So we've got M known to us, fixed and positive, and we know again how many of the n values are less than or equal to M versus how many are greater. So we're not making observations from an exponential distribution. We're making observations either from a Bernoulli distribution or a single observation from a binomial distribution. So the first way we can tackle this is with the Bernoulli distribution. We're observing that y1 through yn, which are IID Bernoulli with some parameter p, these are zeros and ones, and if you add them up, we are observing that the sum of the y's is equal to a k, a constant k. What is p? P is the probability that any one of these y's is equal to 1, and that's going to happen when the corresponding x is less than or equal to m, and x has the exponential distribution with rate lambda, so this is 1 minus e to the minus lambda m. So if we can take our Bernoulli sample and find an MLE for p, we have a relationship between the lambda parameter and the p parameter, and we can use the invariance property of MLEs. Let me actually solve this over here. We have that lambda is a function tau of p, which is -1 over m, the log of 1 minus p. So if we can find the MLE for p, we can plug it in to get the MLE for lambda using the invariance property of MLEs. The MLE for p for the Bernoulli distribution, I bet it would be acceptable to just give this one. It's such a, like, I don't think anyone could, I can't guarantee you what the committee is going to do on the prelim, but I bet it would be acceptable just to say, we know the MLE for p. But let's say we don't. So I have the Bernoulli distribution, p to the y, 1 minus p to the 1 minus y. I have the joint distribution, which comes from multiplying these together, and we get p to the sum of the yi's, 1 minus p, n minus the sum of the yi's. Then we can take this to be the likelihood. Yeah, I'm being lazy and I didn't write my indicators, but I would be dropping them at this point because they are constant when you think of this as a function of p. I'm going to look at the log likelihood and bring down these exponents. And then I'm going to take the derivative with respect to p, and I get the sum of the y's over p minus n minus the sum of the y's over 1 minus p. Set that equal to 0. And if you multiply both sides by p, 1 minus p, on the left side, I get the sum of the y's times 1 minus p minus n minus the sum of the y's. Make a decision, brackets or parentheses, times p. And we get some cancellation. For example, the sum of the y's times negative p and positive p times the sum of the y's are going to cancel. And if you continue to work your way down and solve for p, make everything capital and put a hat on it, we get that this is the sum as I goes from 1 to n of yi over n. And this is y bar. But we didn't observe exactly y bar, but we do know what n is. So we observed p hat. The hat is used for both an estimator, estimator, and an estimate. An estimate is once you've observed it. And we have observed the estimate k over n. So to finish this off, remember we were looking at the lambda, which was -1 over m, the log of 1 minus p. And so the MLE for lambda is the MLE for tau of p. And by the invariance property of MLEs, this is tau of the MLE for p. This is -1 over m, the log of 1 minus the MLE for p. And the observed value is lambda hat equals -1 over m, log of 1 minus k over n. And we have found the MLE for lambda based not on looking at the original values from the exponential distribution, but by saying, looking at each one and saying below m, above m, below m, above m, and sort of recording ones and zeros. So I did say you can also do this with a binomial distribution, and I think I'm actually going to stop here. But if you want to use a binomial distribution, then you only have a sample of size 1. So a new random variable y might be the number of data points from x1 through xn that were observed to be less than or equal to m. And so that has the same probability p that we used in this example, and that one random variable has a binomial distribution with parameters n over p, and you can do the whole procedure with the binomial distribution instead of the Bernoulli, and you'll get the same thing. Yay!